Today we start our new chapter over work and energy. So, what is work? Well, the official definition is work is the product of the magnitudes of the components of a force along the direction of displacement and the displacement. So, simply put, work is equal to force multiplied by the displacement of the object. So you do work on an object, you apply a force, okay? You apply a force and it moves. So work is the force times the displacement. Sounds easy, the definition sounded complicated. It's not. So look at the formula. This should tell you work is only done when the components of a force are parallel to displacement. So you apply a force, and the motion is parallel to the force. Okay, that's what it tells you. When a force and a displacement are not parallel, which I'll show you a picture in a minute what I mean by that. Work can be calculated by multiplying the cosine of the angle between the force and the displacement. So, if you apply an object, let's say you have this apple, and I apply a force to this apple, and the apple moves this way. The force and the motion are parallel. But what if I put a force like this? My force and the apple's movement are not parallel. That's when you use this formula. So the amount of force times the displacement times the cosine of the angle between the force and parallel. Okay, I'll show you a picture in a minute showing that. So if many forces are acting on an object, calculate the net force. So remember we did the diagrams where we showed all the forces and you had to calculate the net force? That's what we're talking about. So net work will equal the net force times the displacement, and if it's at an angle, times the cosine of the angle. So here we go. If I apply a force, let's say we're pulling on this crate, and the force, if you're pulling from this point and you're pulling straight this way, the force is parallel to the movement of the box, no sweat. It's just the force times the direction. But in this case, let's say the rope is attached and we're pulling it towards the ground and the box moves. I mean, there has to be displacement. To calculate the amount of work, it's going to be the amount of force multiplied by the displacement multiplied by the cosine of this angle. Excuse me. Okay, some housekeeping. Work is measured in joules, which a joule is a Newton meter. Remember, force is Newton. The displacement is in meters, so it's Newton meters or joules. It is scalar. Work has no direction. There is no direction, so it's scalar. It's a number. Okay. If force and displacement are in the same direction, work is positive. If they're in the opposite directions, work is negative. So, what do I mean by negative and positive? Okay, if I'm pulling the car and the movement is in the direction I'm pulling it, work is positive. Okay, let's say on this one, quadrant 2, the car is moving forward, but I'm holding it back slightly from going as fast as it could. I am applying a force in the opposite direction, so work is negative. Here, I'm applying a small force to the front of the car, but the car is still moving forward. Again, the force and the direction are in opposite directions. It's negative. And this is the case of pushing a car. The movement is forward and you're pushing it forward. They're both in the same direction, so work is going to be positive. So I told you it was a very short slide, so we're going to go and move to energy. So what is energy? We just talked about work. Well, energy is the energy of an object, and there's two types. There's kinetic energy and there is potential energy. So what's the difference? Kinetic energy is the energy of the object due to its motion. So if it's in motion, it has kinetic energy. Pretty simple. Kinetic energy depends on the speed and the mass. So here is your formula for kinetic energy. So any object in motion has kinetic energy. It's 1/2 multiplied by the mass multiplied by the speed squared. So KE equals 1/2 mass velocity squared. Again, speed, velocity have been interchanged. Energy is also measured in joules. Okay, joules. So, the work kinetic energy theorem. So this tells us how kinetic energy and work are related. The net work done on an object is equal to the change in kinetic energy of that object. The net work is equal to the change in kinetic energy. So, the net work, change of kinetic energy. Here it is. W net is equal to delta, which remember means change of kinetic energy. So the speed of the object and the kinetic energy increase if work is positive. Okay. Speed of an object and kinetic energy decrease if work is negative. Kinetic energy is the work an object can do as it comes to rest. Okay. And kinetic energy is the amount of energy stored in an object. So, all objects have energy. It's how we're looking at it. So, let's back up. Speed of an object and the kinetic of the kinetic energy increase if work is positive. So, I'm applying a force in the direction of the movement. Work is positive. You could basically say it's probably speeding up. Okay. So if an object is moving forward and I'm applying a force to slow it down, work is negative. It's slowing down. Kinetic energy is the work an object can do as it comes to rest. So if it's in motion, it has kinetic energy. The other kind is potential energy. So you have kinetic and potential. Potential energy is the energy associated with an object due to its position. So you're like, what? Due to its position? Okay, it's relative and based on a frame of reference. It's abbreviated PE, measured in joules, and there's two kinds of potential energy, gravitational and potential. So let's go back to the part where it's due to the position of an object. So let's say we have an apple up here. It's not moving. It has gravitational potential energy. It has the potential to do work. Okay. It's based on its height. If you look at the equation, it's the mass of the apple times g, which is 9.81, multiplied by the height. How far above the ground is the apple positioned? Gravitational potential energy, again, is mass times free fall acceleration times height. As the objects fall, gravitational potential energy is converted to kinetic. So we're saying an object at rest but not sitting on the ground has potential energy, and in this case, it's gravitational potential energy. If I were to drop it as it falls, that potential energy is converted into kinetic energy. Until that split second before it hits the ground, as it hits the ground, it is 100% potential energy, and then as it rests on the ground, not moving, and it has no height, the energy is zero. So, based on this logic, apple at this position has a higher potential energy than the apple at this position. Height is greater. If you calculate it out, height is a bigger number, and it'll have higher potential. It has the same mass as here. G is the same here as here. The only thing difference is the height. So it's based on height. So this rock, the top rock, it's not falling, it's standing in one place. It has potential energy. And the amount of potential energy is based on the mass multiplied by the height multiplied by G. So again, this is the same difference if I were to drop a ball off the building. It would have a higher potential before I dropped it here than it would here, based on height. So now we're going to talk about elastic potential energy. So we had gravitational potential energy, or the potential to do work. Now elastic. If we have something that is stretchy, like let's go with a spring, okay? This could be elastic or rubber band, something that can be stretched and compressed. The potential energy in a stretched or compressed elastic object. The energy of the spring, it has energy. It wants to either collapse or pull. So the relaxed length, that would be the length of a spring with no forces acting on it. It's just the resting length. As the spring is compressed or extended, okay, the amount of potential energy changes. So, depending on the spring, okay, we're going to talk about springs in as if we're going to compress it. If you've ever played with the spring, like from your door or whatever, from the screen door, not all springs compress with the same amount of energy. So depending on what the spring is made of, if it's metal, is it plastic, is it glass, what is the spring? Different materials will stretch and compress differently. So we come up with a spring constant. A spring constant is basically you're accounting for what the spring is made up of. It's a parameter that expresses how resistant a spring is to being compressed or stretched. So we have to take into consideration what the spring is made of. So the elastic potential energy is 1/2 multiplied by the spring constant multiplied by the distance it's either stretched or compressed. Here it is at the bottom. The potential, elastic potential of a spring is 1/2 the spring constant K, which will be a nerd number in a nerd book. You don't have to calculate it originally. And then times the distance it stretched or compressed squared. So it's just what I've been saying with the spring. This is elastic. You can compress it. You can compress it. You can stretch it out. The distance it's compressed or stretched times the spring constant times K, the distance squared. And that is it. So we have kinetic energy, we have two types of energy. We have kinetic energy and we have potential energy. We have potential energy, we have two types. Is it gravitational or is it elastic? Gravitation is the potential energy based on how high something is located off the ground. Okay. Elastic potential has to do with stretchy things, and it's how much an object is compressed or stretched. And then we have the kinetic energy, which is the energy of any object that's actually moving. Okay, get your notes copied into your journal and send me a picture of your notes. Thanks.